In RSA cryptography, large numbers and the calculations that you can do with them, and also the calculations you cannot do with them in the lifetime of the universe, play a critical role. Some of what I say here will make more sense after you look at the videos in the following sections, in particular implementation of RSA and RSA in practice. So RSA has three main parts. It has the setup in making available your public key, which anybody then can use to encrypt messages for you. The actual encryption and decryption process, where people encrypt messages and you, after receiving the encrypted message, can decrypt it. And another critical part, of course, is attempts to crack RSA. And in each of these, computations with large numbers play an essential role. First of all, setting up RSA. So my setting up, or Bob's setting up of RSA for him, involves selecting two random prime numbers, each 150 digits long or more. Nowadays, typically, they may be as much as 300 digits long, multiplying them to give a number n, which will then be 600 digits long. And all of this takes just a second or so. And you'll see this if you go to the section prime numbers, then frequency of primes, and the slide looking for big primes. The next aspect is the encryption and decryption process. And in both cases, this involves a calculation of the form find n to the b modulo n, where n was the 300 or 600 digit number we mentioned up in here. And n, b and n may be, again, have as many as 300 digits or more. And each time the process is done, and whether it's encryption or decryption, you use different n's and b's. To do these calculations, Maple again will just take a second or so, and of course fast computers and programs dedicated to these calculations will be much faster than that even. So if you go to the section modular arithmetic, modular operations, example of exponentiation, you'll see the process that is used to do this. Finally, attempts to crack RSA. Now, at least naively, there would be two possibilities. One would be, given the number n, which is publicly available, factorize it into the two prime numbers, which everybody knows are there, in the sense that everybody knows this number n, publicly available, whether it's 300 or 600 digits, is a product of two prime numbers roughly equal size. But to actually do that calculation and to go through all the possibilities and find the factors would take, with current computing technology, the lifetime, more than the lifetime of the universe. Now, maybe somebody will find a faster method, but I think very few people believe that, because these methods are connected with a whole lot of other sorts of problems, which, if fast methods were found, would really revolutionize computer science and mathematics and just our everyday life. So nobody believes, or I should say no expert probably believes, that it's possible to actually factor these numbers, let's say 300 digits even, at the moment, with current computing technology in the foreseeable future. And once one could do this, then one would just increase the size. Doesn't make much difference to these calculations, but each time you add an extra digit, you send up by a factor, more or less, the time, a factor bigger than 1, the amount of time required to do the computation. Another possibility would be to just take the encrypted message, which again, for example, if Alice is sending Bob a message, the encrypted message can be made publicly available, and then to just check all possible numbers or messages that may have given that encrypted message. Again, this is believed to be equally difficult in terms of calculation time to the factorizing problem. So both are essentially impossible to do, whether it's reversing the encryption process or factorizing the initial publicly available number n. And the reason, of course, that factorising n would allow us to crack the RSA method is that the number n is what's used in doing the setup process here. And this is discussed later on under RSA cryptography, that's this section, and then RSA in practice, and why RSA is effective, if you look at that particular slide.